Dear children, we are going to study the chapter 13, Kinetic Theory. Kinetic theory explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms or molecules. And you studied in the lower classes that in the case of solids, the molecules are very close together and the intermolecular force of attraction is very high. But in the case of liquids, the intermolecular force of attraction is less than that of the solids, and the distance between the molecules is larger than that of the solid. But in the gases, the intermolecular force of attraction is less than that of the solid and the gases, and the molecules are rapidly moving. Okay, so these things are explained in this chapter, Kinetic Theory. So first we are going to see some laws related to this kinetic theory. The first one, that is the Boyle's law. And this is a fundamental gas law discovered by Robert Boyle in 1662. It states that volume of a given mass of a gas is inversely proportional to its pressure, and there the temperature remains constant. Mathematically, we can write like this, that is V is proportional to 1 by P, that is the volume is inversely proportional to its pressure, or we can write V equal to K by P, where K is a constant. So we can write PV equal to K. When we are drawing the graph between P and V, there P is inversely proportional to V, so we get a parabolic graph like this. And from the equation we know that is P is directly proportional to 1 by V. So here you can understand that from this equation we can write P proportional to 1 by V. So P and 1 by V are directly proportional to each other. So P versus 1 by V graph is a straight line graph where the temperature remains constant. Clear? Second law, Charles' law. This law gives the relation between volume and temperature of a gas at constant pressure, and it was discovered by Alexander Charles in 1787. It states that if the pressure remains constant, the volume of a given mass of a gas increases or decreases by 1 by 273.15 of its volume at 0 degree Celsius. For each 1 degree Celsius, there is a rise or fall of temperature. In another way, we can define this Charles' law. It states that pressure remains constant. The volume of a given mass of a gas is directly proportional to its absolute temperature. That we defined the first statement. This statement is very easier, so you study this. Okay, it states that is the Charles' law states that pressure remains constant. Then the volume of a given mass of a gas is directly proportional to its absolute temperature. That we can write like this, V proportional to T, then V by T equal to constant. So what is the nature of the graph between V and T? That is straight line where P remains constant. Okay, V versus T graph is a straight line graph. Then Gay-Lussac's law. This law gives the relation between pressure and temperature of a gas. It was discovered by Joseph Gay-Lussac. It states that volume remaining constant, the pressure of a given mass of a gas is directly proportional to its absolute temperature. That we can write like this, P proportional to T. P by T equal to constant. So these are some of the important laws you want to study in the chapter Kinetic Theory. Clear? Next topic, expression for pressure exerted by a gas. There are some assumptions for deriving the expression for the pressure exerted by the gas. First one, all gases consist of molecules and that molecules are rigid and should be elastic. Then second one, about the size of the molecule. The size of the molecule is negligible compared with the average distance between the molecules present in the container. Then the third one, the molecules are in a state of continuous motion, that is in random motion, moving in all directions with the possible velocities. So the molecules should be in random motion. Then the fourth one, during the random motion, the molecules collide with one another and with the walls of the vessel. During collision, their velocities are changed in magnitude and direction. Then the fifth one, the collisions are perfectly elastic and there are no force of attraction or repulsion between the molecules. Then another one assumption, it should obey the Newton's law of motion. So on the basis of these assumptions, we are considering an ideal gas enclosed in a cubical vessel. The sides of the cube are parallel to x, y and z axis. This is the x axis and this is the y axis and this is the z axis. So the sides of the cubes are parallel to the x axis and y axis and z axis. Then we can consider n, small n be the number of molecules present in the container per unit volume and small m be the mass of each molecule. Then if you are considering a molecule, it moves with velocity Vx, Vy and Vz, and it hits the walls of the container in this shaded portion, in this area A. And when it hits on the walls of this shaded area, then it rebounds with the same velocity because collision is elastic. When it hits on the walls, then it rebounds with the same velocity. So here the molecule is moving towards the wall with a velocity Vx, Vy, Vz and hits on the walls, then it rebounds with a velocity minus Vx, Vy and Vz. Here the y and z components of V do not change, but the x component reverses because it moves along the, or it rebounds along the x-axis. So the momentum of the molecule we can write, that is the mvx, momentum equal to mvx. If it reverses, then its momentum changes into minus mvx. So what is the change in momentum? So what is the change in momentum? That is final momentum minus initial momentum. So here the final momentum is minus mvx minus initial momentum mvx. So we get the minus 2mvx. This is the change in momentum of the molecule when it hits on the walls of the container in this shaded portion. As the collision is perfectly elastic, so the same amount of momentum is imparted to wall in each collision, that we can note it as, that is the 2mvx, because the collision is elastic. So it rebounds, or when it moves, this is the momentum when it moves along the negative axis, and this is the momentum when it is going to hit on the wall, imparted to the wall in each collision, that is the 2mvx. So in a time, if you consider a small time delta t, the molecules travel through a distance Vx into delta t along the x-axis. Okay, for a small time delta t, the molecules move along the x-axis with a distance Vx into delta t. So all the molecules which are situated in the shaded portion within this distance or less than this distance will hit the wall. Therefore, we can say that the molecules present in the volume AVX delta T, that is area into the distance, that is the volume. So, if the molecules present in this volume will hit on the wall, that is in the shaded portion. So, the number of molecules, so our aim is to find out the pressure exerted by the gas. So, the number of molecules, number of molecules hitting the wall, number of molecules hitting the wall equal to small n into AVX delta T. Number of molecules hitting the wall in that volume, that is the NaVX into delta T. So, due to this random motion of the molecules, all these molecules, that is, this is the total number of molecules hitting the wall, but all these molecules do not move along the positive x-axis. Half of the molecule will move along the negative x-axis. So, we can write number of molecules, number of molecules move along the positive x-axis, that is towards the shaded portion, that is equal to half of this molecule, that we can write half into NaVX delta T. So, half of these molecules move along the x-axis and hit on the wall. Then, what is the change in momentum of the single molecule is what? 2mvx along the x-axis. So, total change in momentum transferred to the wall in time delta T. How can we write like that? We can write total change in momentum. Total change in momentum transferred to the wall, transferred to the wall in time delta T, that is equal to, what is the momentum of the single molecule, that is 2mvx into half the number of molecules are hitting on the wall, that is into half into NaVX delta T. So, this is the total change in momentum transferred to the wall, that is on the shaded portion. So, here 2 and 2 will cancel. So, we get NmVx square A delta T. This is the total change in momentum imparted to the wall in time delta T. Then from Newton's law, we can write force equal to rate of change of momentum. So, here the momentum is what? Nmvx square A delta T divided by delta T. So, we get force equal to Nmvx square A. Clear? Then we can write the pressure exerted on the walls of the container, that is on the shaded portion, equal to force divided by the area. So, the area is that shaded portion. So, that is equal to Nmvx square A divided by A, that is equal to Nmvx square. So, this is the pressure exerted on the wall, and that is on the shaded portion. As the molecules are moving with different velocities, so we can replace this Vx square by its average value. Here the molecules are moving with different velocities. So we can write this Vx square equal to average value of velocity of molecules in the x direction. So we can write the pressure P equal to Nmvx square bar. Clear? Then, if the gas is isotropic, so the molecular velocities are almost equally distributed in different directions. So, in symmetry, we can write Vx square bar is equal to Vy square bar is equal to Vz square bar. That is equal to 1 by 3 of Vx square bar plus Vy square bar plus Vz square bar. So, what is this value? That is the V square bar, average value of all the velocities of all the molecules in different directions. So, we can write 1 by 3 V square bar. So, this V square bar is the mean square velocities of all the molecules. Then we can substitute this Vx square bar in this above equation pressure, that is P equal to 1 by 3 N M V square bar. This is the pressure exerted by the molecules on a particular area. So, V square bar is the velocities of all the molecules in different directions. So, here this Nm, that is the total mass of the molecule per unit volume, that is equal to the density, that we can write here rho equal to mass by volume. You know that density equal to mass by volume. So, here mass is the total mass of all the molecules, that is rho equal to Nm divided by per unit volume. So, that is rho equal to Nm. So, here we can write P equal to 1 by 3 rho V square bar. So, this is the, so we can write this pressure in terms of the densities. Okay. According to Pascal's law, a gas transmits pressure equally in all directions, like as we studied in the mechanics of fluid. So, this two equations, okay, this equation 1 and equation 2 give the pressure exerted by the gas in any direction. Clear? So, these are the important topics in the chapter kinetic theory. Clear?